Today we're going to look at more related rates with surface area. We're going to do two parts with surface area, and then we're going to look at volume when we're dealing with cones. So for number one, the volume of a sphere is expanding at a rate of 3 centimeters cubed per minute. Okay. So this time we're dealing with a sphere. And we know we're dealing with volume because it's cubed and it tells us volume. Okay, so for part A, how fast is the radius changing when the radius is 1 centimeter? So my equation is going to be volume equals, the volume of a sphere is 4/3 pi r cubed. Then our derivative, the derivative of v, dv dt, equals the derivative over here. This is just power rule, so bring the 3 in front. So 4/3 times 3 is just going to be 4 pi. This will now be r squared dr dt. They want to know how fast the radius is changing, so that's our dr dt. Okay. So what I'm going to plug in, okay, the sphere is expanding, so that means this is positive. So I'll plug in a positive 3 for dv dt. Then 4 pi, my radius is 1, so that'll be 1 squared dr dt. So I'm going to do 1 squared, which was 1, times 4 is going to be 4 pi dr dt. And then to solve for dr dt, I'm just going to do 3 divided by 4 pi. And I'm going to leave my answer like this since I'm not done, since I'm going to move on to part B. So instead of keeping track of this decimal on the calculator, I'm just going to leave it in terms of pi. Okay? And then my units are going to be centimeters per second. Okay, it's regular centimeters because we're dealing with the radius now. Now for part B. Okay. How fast is the surface area changing? So now I'm going to switch my equation to the area equation. Then my derivative, the derivative of A is dA dt. Power rule again over here, so 2 times 4 pi would be 8 pi r to the first dr dt. Now they're asking how fast the surface area is changing. So that's dA dt. So here to solve for dA dt, I'm going to plug in a 1 from r, and then I'm going to take this number over here that I got for r and plug in the 3 over 4 pi. So this whole part over here is over 1, so I'm going to multiply my numerators. That'll give me 24 pi. My denominator will be 4 pi, so the pi's are going to cancel out. 4 divided by 24 is going to give me 6. So the rate of change for the area is going to be 6, and now it's going to be centimeters squared, because we're dealing with area, per second. So it's always going to be a two-part question anytime they give you something about the volume, but they ask for something about the area. So it won't necessarily be broken up into 2 parts. Okay, but if what they give you is volume and what they ask for is area, that tells you you're going to have to go through 2 steps. Okay, and vice versa. If they gave us area but asked about volume, we'd have to start with the area equation. Then we'd have to do a second part with the volume equation. So let's look at another one similar to this. The surface area of a cube is decreasing at a rate of 1 meter squared per minute. So I'm going to go ahead and put a little negative here so I remember. How fast is the volume decreasing when the edge is 10 meters? Okay, so I know that this is going to be a two-part one because what they gave me is area, so that means I have to use my area equation. But what they're asking for is volume, so I'm also going to have to use my volume equation. So first thing I'm going to do is draw my cube. Okay, the edge is just that side length right there. Okay, so what equation you start with is what they give you. Okay, so they gave us the rate of change for the surface area. So for the first part, the equation I start with has to be the surface area one, because that's what we're given. So whatever you're given is the equation you start with. Okay. So then I'll take the derivative of this. That's dA dt. This will be 12s ds dt. Okay. Now what they're asking for is the volume. Well, I can't solve for the volume at this step because I'm dealing with area. So I'm just going to take this derivative equation, solve for whatever I'm missing. Okay, so I know the rate of change for the area. So dA dt is going to be -1 because it's decreasing. They tell us the edge, which is the side, is 10. So that'll be ds dt. Okay. So I'm going to go ahead and solve for ds dt. So this will give me 120. So I'm just going to have -1 over 120. And this would be meters per minute. Since we're just dealing with the side length, that's regular meters. Okay. So the reason we have to find this is now we're going to have to set up a new equation for the volume. So we're going to need this ratio right here, the ds dt, to solve for the rate of change for the volume. Okay. So now it's kind of like we're starting a new problem with our volume equation. So that'll be 4/3 pi r cubed. Then our derivative, that'll be dv dt equals 3 times 4, oh, sorry, I'm using the wrong equation. We're dealing with a cube, not a sphere. So this will be volume equals s cubed. So then our derivative, dv dt, is going to be 3s squared ds dt. Then what we're looking for is dv dt. So that'll be 3 times 10 squared, so this is our s still, times ds dt, that's what we just found right here. So -1 over 120. So that'll give me 300 times -1, so -300 over 120 is going to give me the rate of change for the volume to be -2.5. Since it's volume, it'll now be meters cubed per minute.